Electromagnetic waves. Introduction. In Chapter 4, we learnt that an electric current produces magnetic field and that two current-carrying wires exert a magnetic force on each other. Further, in Chapter 6, we have seen that a magnetic field changing with time gives rise to an electric field. Is the converse also true? Does an electric field changing with time give rise to a magnetic field? James Clerk Maxwell, 1831–1879, argued that this was indeed the case. Not only an electric current but also a time-varying electric field generates magnetic field. While applying the Ampere's circuitale law to find magnetic field at a point outside a capacitor connected to a time-varying current, Maxwell noticed an inconsistency in the Ampere's circuitale law. He suggested the existence of an additional current, called by him the displacement current, to remove this inconsistency. Maxwell formulated a set of equations involving electric and magnetic fields, and their sources, the charge and current densities. These equations are known as Maxwell's equations. Together with the Lorentz force formula, they mathematically express all the basic laws of electromagnetism. The most important prediction to emerge from Maxwell's equations is the existence of electromagnetic waves, which are coupled, time-varying electric and magnetic fields that propagate in space. The speed of the waves, according to these equations, turned out to be very close to the speed of light. That's about 3 × 10⁸ meters per second, obtained from optical measurements. This led to the remarkable conclusion that light is an electromagnetic wave. Maxwell's work thus unified the domain of electricity, magnetism and light. Hertz, in 1885, experimentally demonstrated the existence of electromagnetic waves. Its technological use by Marconi and others led in due course to the revolution in communication that we are witnessing today. In this chapter, we first discuss the need for displacement current and its consequences. Then we present a descriptive account of electromagnetic waves. The broad spectrum of electromagnetic waves, stretching from gamma rays, wavelength of 10⁻⁻12 meters, to long radio waves, wavelength of 10⁻⁶ meters, is described. 8.2 Displacement current. We have seen in Chapter 4 that an electrical current produces a magnetic field around it. Maxwell showed that for logical consistency, a changing electric field must also produce a magnetic field. This effect is of great importance because it explains the existence of radio waves, gamma rays and visible light, as well as all other forms of electromagnetic waves. To see how a changing electric field gives rise to a magnetic field, let us consider the process of charging of a capacitor and apply Ampere's circuitale law given by the equation 8.1 to find magnetic field at a point outside the capacitor. Figure 8.1 shows a parallel plate capacitor C, which is a part of circuit through which a time-dependent current I, T, flows. Let us find the magnetic field at a point such as P, in a region outside the parallel plate capacitor. For this, we consider a plane circular loop of radius r whose plane is perpendicular to the direction of the current-carrying wire, and which is centered symmetrically with respect to the wire, figure 8.1 From symmetry, the magnetic field is directed along the circumference of the circular loop and is the same in magnitude at all points on the loop, so that if B is the magnitude of the field, the left side of equation 8.1 is B, 2πr. So we have the equation 8.2. Now, consider a different surface, which has the same boundary. This is a pot-like surface, figure 8.1, B, which nowhere touches the current, but has its bottom between the capacitor plates. Its mouth is the circular loop mentioned above. Another such surface is shaped like a tiffin box, without the lid, figure 8.1, C. On applying Ampere's circuitale law to such surfaces with the same perimeter, we find that the left-hand side of equation 8.1 has not changed, but the right-hand side is 0 and not μI, since no current passes through the surface of figure 8.1, B, and C. So we have a contradiction. Calculated one way, there is a magnetic field at a point P. Calculated another way, the magnetic field at P is 0. Since the contradiction arises from our use of Ampere's circuitale law, this law must be missing something. The missing term must be such that one gets the same magnetic field at point P, no matter what surface is used. We can actually guess the missing term by looking carefully at figure 8.1, C. Is there anything passing through the surface S between the plates of the capacitor? Yes, of course, the electric field. If the plates of the capacitor have an area A and a total charge Q, the magnitude of the electric field E between the plates is Q by A by epsilon naught, see equation 2.41. The field is perpendicular to the surface S of figure 8.1, c. It has the same magnitude over the area A of the capacitor plates, and vanishes outside it. So what is the electric flux phi E through the surface S? Using Gauss's law, it is given by the equation 8.3. Now if the charge Q on the capacitor plates changes with time, there is a current I equals dQ by dt, so that using equation 8.3, we have the below equation. This implies that for consistency, equation 8.4 is given. This is the missing term in Ampere's circuitale law. If we generalize this law by adding to the total current carried by conductors through the surface, another term which is epsilon naught times the rate of change of electric flux through the same surface, the total has the same value of current I. For all surfaces. If this is done, there is no contradiction in the value of B obtained anywhere using the generalized Ampere's law. B at the point P is non-zero no matter which surface is used for calculating it. B at a point P outside the plates, figure 8.1a, is the same as at a point M just inside, as it should be. The current carried by conductors due to flow of charges is called conduction current. The current, given by equation 8.4, is a new term, and is due to changing electric field, or electric displacement, an old term still used sometimes. It is, therefore, called displacement current or Maxwell's displacement current. Figure 8.2 shows the electric and magnetic fields inside the parallel plate capacitor discussed above. The generalization made by Maxwell then is the following equation. The source of a magnetic field is not just the conduction electric current due to flowing charges. But also the time rate of change of electric field. More precisely, the total current I is the sum of the conduction current denoted by IC, and the displacement current denoted by ID. So we have the equation 8.5. In explicit terms, this means that outside the capacitor plates, we have only conduction current IC equals I and no displacement current, that is ID equals 0. On the other hand, inside the capacitor, there is no conduction current, that is IC equals 0, and there is only displacement current, so that ID equals I. The generalized and correct Ampere's circuitale law has the same form as equation 8.1, with one difference. The total current passing through any surface of which the closed loop is the perimeter, is the sum of the conduction current and the displacement current. The generalized law is given by the equation 8.6 and is known as Ampere-Maxwell law. In all respects, the displacement current has the same physical effects as the conduction current. In some cases, for example, steady electric fields in a conducting wire, the displacement current may be zero since the electric field E does not change with time. In other cases, for example, the charging capacitor above, both conduction and displacement currents may be present in different regions of space. In most of the cases, they both may be present in the same region of space, as there exists no perfectly conducting or perfectly insulating medium. Most interestingly, there may be large regions of space where there is no conduction current, but there is only a displacement current due to time-varying electric fields. In such a region, we expect a magnetic field, though there is no conduction current source nearby. The prediction of such a displacement current can be verified experimentally. For example, a magnetic field, say at point M, between the plates of the capacitor in figure 8.2, can be measured and is seen to be the same as that just outside, at P. The displacement current has, literally, far-reaching consequences. One thing we immediately notice is that the laws of electricity and magnetism are now more symmetrical. Faraday's law of induction states that there is an induced EMF equal to the rate of change of magnetic flux. Now, since the EMF between 2 points 1 and 2 is the work done per unit charge in taking it from 1 to 2, the existence of an EMF implies the existence of an electric field. So, we can rephrase Faraday's law of electromagnetic induction by saying that a magnetic field, changing with time, gives rise to an electric field. Then, the fact that an electric field changing with time gives rise to a magnetic field, is the symmetrical counterpart, and is a consequence of the displacement current being a source of a magnetic field. Thus, time-dependent electric and magnetic fields give rise to each other. Faraday's law of electromagnetic induction and Ampere-Maxwell law give a quantitative expression of this statement, with the current being the total current, as in equation 8.5. One very important consequence of this symmetry is the existence of electromagnetic waves, which we discuss qualitatively in the next section. Electromagnetic waves. Sources of electromagnetic waves. How are electromagnetic waves produced? Neither stationary charges nor charges in uniform motion, steady currents, can be sources of electromagnetic waves. The former produces only electrostatic fields, while the latter produces magnetic fields that, however, do not vary with time. It is an important result of Maxwell's theory that accelerated charges radiate electromagnetic waves. The proof of this basic result is beyond the scope of this book, but we can accept it on the basis of rough, qualitative reasoning. Consider a charge oscillating with some frequency. An oscillating charge is an example of accelerating charge. This produces an oscillating electric field in space, which produces an oscillating magnetic field, which in turn is a source of oscillating electric field, and so on. The oscillating electric and magnetic fields thus regenerate each other, so to speak, as the wave propagates through the space. The frequency of the electromagnetic wave naturally equals the frequency of oscillation of the charge. The energy associated with the propagating wave comes at the expense of the energy of the source, the accelerated charge. From the preceding discussion, it might appear easy to test the prediction that light is an electromagnetic wave. We might think that all we needed to do was to set up an AC circuit in which the current oscillate at the frequency of visible light, say, yellow light. But, alas, that is not possible. The frequency of yellow light is about 6 times 10 power 14 Hz, while the frequency that we get even with modern electronic circuits is hardly about 10 power 11 Hz. This is why the experimental demonstration of electromagnetic wave had to come in the low frequency region, the radio wave region, as in the Hertz's experiment. Hertz's successful experimental test of Maxwell's theory created a sensation and sparked off other important works in this field. Two important achievements in this connection deserve mention. 7 years after Hertz, Jagdish Chandra Bose, working at Calcutta, now Kolkata, succeeded in producing and observing electromagnetic waves of much shorter wavelength, 25 mm to 5 mm. His experiment, like that of Hertz's, was confined to the laboratory. At around the same time, Guglielmo Marconi in Italy followed Hertz's work and succeeded in transmitting electromagnetic waves over distances of many kilometers. Marconi's experiment marks the beginning of the field of communication using electromagnetic waves. Nature of electromagnetic waves. It can be shown from Maxwell's equations that electric and magnetic fields in an electromagnetic wave are perpendicular to each other, and to the direction of propagation. It appears reasonable, say from our discussion of the displacement current. Consider figure 8.2. The electric field inside the plates of the capacitor is directed perpendicular to the plates. The magnetic field this gives rise to via the displacement current is along the perimeter of a circle parallel to the capacitor plates. So B and E are perpendicular in this case. This is a general feature. In figure 8.3, we show a typical example of a plane electromagnetic wave propagating along the z direction. The fields are shown as a function of the z coordinate at a given time t. The electric field E is along the x-axis and varies sinusoidally with z at a given time. The magnetic field Y is along the y-axis and again varies sinusoidally with z. The electric and magnetic fields X and Y are perpendicular to each other and to the direction z of propagation. We can write X and Y as in equation 8.7a and b. Here k is related to the wavelength lambda of the wave by the usual equation. 8.8. And omega is the angular frequency. K is the magnitude of the wave vector or propagation vector. K and its direction describes the direction of propagation of the wave. The speed of propagation of the wave is omega by k. Using equations 8.7 a and b, For X and by in Maxwell's equations, one finds that omega equals ck, where c equals I by square root of mu naught epsilon naught. The relation omega equals ck is the standard one for waves. This relation is often written in terms of frequency, nu, and wavelength, lambda, as given below. It is also seen from Maxwell's equations that the magnitude of the electric and the magnetic fields in an electromagnetic wave are related as B0 equals E0 by c. We here make remarks on some features of electromagnetic waves. They are self-sustaining oscillations of electric and magnetic fields in free space or vacuum. They differ from all the other waves we have studied so far, in respect that no material medium is involved in the vibrations of the electric and magnetic fields. But what if a material medium is actually there? We know that light, an electromagnetic wave, does propagate through glass, for example. We have seen earlier that the total electric and magnetic fields inside a medium are described in terms of a permittivity epsilon and a magnetic permeability mu. These replace epsilon naught and mu naught in the description to electric and magnetic fields in Maxwell's equations, with the result that in a material medium of permittivity epsilon and magnetic permeability mu, the velocity of light is given by the equation 8.11. Thus, the velocity of light depends on electric and magnetic properties of the medium. We shall see in the next chapter that the refractive index of one medium with respect to the other is equal to the ratio of velocities of light in the two media. The velocity of electromagnetic waves in free space or vacuum is an important fundamental constant. It has been shown by experiments on electromagnetic waves of different wavelengths that this velocity is the same, independent of wavelength, to within a few meters per second, out of a value of 3 × 10⁸ meters per second. The constancy of the velocity of m waves in vacuum is so strongly supported by experiments, and the actual value is so well known now that this is used to define a standard of length. The great technological importance of electromagnetic waves stems from their capability to carry energy from one place to another. The radio and TV signals from broadcasting stations carry energy. Light carries energy from the sun to the earth, thus making life possible on the earth. Electromagnetic spectrum. At the time Maxwell predicted the existence of electromagnetic waves, the only familiar electromagnetic waves were the visible light waves. The existence of ultraviolet and infrared waves was barely established. By the end of the 19th century, X-rays and gamma rays had also been discovered. We now know that electromagnetic waves include visible light waves, X-rays, gamma rays, radio waves, microwaves, ultraviolet and infrared waves. The classification of M waves according to frequency is the electromagnetic spectrum, figure 8.4. There is no sharp division between one kind of wave and the next. The classification is based roughly on how the waves are produced and/or detected. We briefly describe these different types of electromagnetic waves, in order of decreasing wavelengths. Radio waves. Radio waves are produced by the accelerated motion of charges in conducting wires. They are used in radio and television communication systems. They are generally in the frequency range from 500 kHz to about 1000 MHz. The AM, amplitude modulated, band is from 530 kHz to 1710 kHz. Higher frequencies up to 54 MHz are used for short wave bands. TV waves range from 54 MHz to 890 MHz. The FM, frequency modulated, radio band extends from 88 MHz to 108 MHz. Cellular phones use radio waves to transmit voice communication in the ultra-high frequency UHF band. How these waves are transmitted and received is described in Chapter 15. Microwaves. Microwaves, short wavelength radio waves, with frequencies in the gigahertz (GHz) range, are produced by special vacuum tubes, called klystrons, magnetrons and gun diodes. Due to their short wavelengths, they are suitable for the radar systems used in aircraft navigation. Radar also provides the basis for the speed guns used to time fast balls, tennis serves, and automobiles. Microwave ovens are an interesting domestic application of these waves. In such ovens, the frequency of the microwaves is selected to match the resonant frequency of water molecules so that energy from the waves is transferred efficiently to the kinetic energy of the molecules. This raises the temperature of any food containing water. Infrared waves. Infrared waves are produced by hot bodies and molecules. This band lies adjacent to the low frequency or long wavelength end of the visible spectrum. Infrared waves are sometimes referred to as heat waves. This is because water molecules present in most materials readily absorb infrared waves. Many other molecules, for example, CO2, NH3, also absorb infrared waves. After absorption, their thermal motion increases, that is, they heat up and heat their surroundings. Infrared lamps are used in physical therapy. Infrared radiation also plays an important role in maintaining the Earth's warmth or average temperature through the greenhouse effect. Incoming visible light, which passes relatively easily through the atmosphere, is absorbed by the Earth's surface and re-radiated as infrared, longer wavelength, radiations. This radiation is trapped by greenhouse gases such as carbon dioxide and water vapor. Infrared detectors are used in Earth satellites, both for military purposes and to observe growth of crops. Electronic devices, for example semiconductor light-emitting diodes, also emit infrared and are widely used in the remote switches of household electronic systems such as TV sets, video recorders and hi-fi systems. Visible rays. It is the most familiar form of electromagnetic waves. It is the part of the spectrum that is detected by the human eye. It runs from about 4 times 1014 Hz to about 7 times 1014 Hz, or a wavelength range of about 700 to 400 nanometers. Visible light emitted or reflected from objects around us provides us information about the world. Our eyes are sensitive to this range of wavelengths. Different animals are sensitive to different range of wavelengths. For example, snakes can detect infrared waves, and the visible range of many insects extends well into the ultraviolet. Ultraviolet rays. It covers wavelengths ranging from about 4 times 10 power minus 7 meters, 400 nanometers, down to 6 times 10 power minus 10 meters, 0.6 nanometers. Ultraviolet (UV) radiation is produced by special lamps and very hot bodies. The sun is an important source of ultraviolet light, but fortunately, most of it is absorbed in the ozone layer in the atmosphere at an altitude of about 40 to 50 kilometers. UV light in large quantities has harmful effects on humans. Exposure to UV radiation induces the production of more melanin, causing tanning of the skin. UV radiation is absorbed by ordinary glass. Hence, one cannot get tanned or sunburned through glass windows. Welders wear special glass goggles or face masks with glass windows to protect their eyes from large amount of UV produced by welding arcs. Due to its shorter wavelengths, UV radiations can be focused into very narrow beams for high-precision applications such as LASIK, laser-assisted in situ keratomylosis, eye surgery. UV lamps are used to kill germs in water purifiers. Ozone layer in the atmosphere plays a protective role, and hence its depletion by chlorofluorocarbons, CFCs, gas, such as freon, is a matter of international concern. X-rays. Beyond the UV region of the electromagnetic spectrum lies the X-ray region. We are familiar with X-rays because of its medical applications. It covers wavelengths from about 10 power minus 8 meters, 10 nanometers, down to 10 power minus 13 meters, 10 to 4 nanometers. One common way to generate X-rays is to bombard a metal target by high-energy electrons. X-rays are used as a diagnostic tool in medicine and as a treatment for certain forms of cancer. Because X-rays damage or destroy living tissues and organisms, care must be taken to avoid unnecessary overexposure. Gamma rays. They lie in the upper frequency range of the electromagnetic spectrum and have wavelengths of from about 10 power minus 10 meters to less than 10 power minus 14 meters. This high-frequency radiation is produced in nuclear reactions and also emitted by radioactive nuclei. They are used in medicine to destroy cancer cells. Table 8.1 summarizes different types of electromagnetic waves, their production and detections. As mentioned earlier, the demarcation between different regions is not sharp and there are overlaps.